Welcome back to Physics 141 online. Today I'll give an introduction to the subject of mechanics. Here's the outline for where we're going in this part of the course. Kinematics and mechanics. I'll discuss the connection between those two subjects, give an introduction to Newton's laws of motion, talk about common forces in nature, and then move on to illustrate problem solving using Newton's laws, and then some special situations involving frictional forces, and then ultimately the dynamics of circular motion. Kinematics, which is what we've been studying up till this point in the course, is simply concerned with the relationship for a moving object between its position, velocity, and acceleration, of course in terms of the time. And kinematics doesn't really worry about the origin of the motion, what caused an object to be accelerating or moving, and that's where mechanics comes in. Mechanics is the study of the relationship between forces that an object experiences and then the motion or change in motion that results from the action of those forces. To give a little bit of historical background, because it's important for us to understand why sometimes we have misconceptions about the relationship between forces and motion. From the time of the ancient Greeks, almost until the time of Galileo in the late 1500s and early 1600s, the so-called natural state of an object was thought to be at rest. And so just based on this assumption or this philosophy, it was assumed there was a direct connection between the force on an object, whatever an external agent might do to it, and the object's velocity. And this makes sense in our everyday life. If there is a box sitting on the ground, if I want to get it to move, I have to push on it, right? So it seems like it's natural to connect force and velocity. And as a result, it was thought that a non-zero force implied a non-zero velocity, and so on. That seems to us just to be like common sense. And yet, Galileo and Newton showed that that idea is wrong. And it's important for us to understand that because it's such a persistent idea that even today, many of us still have. Galileo, his genius in the realm of physics lie in carrying out thought experiments. And this was one of the things that really enabled him to develop what he called the Principle of Inertia, which was an early version of Newton's first law of motion. He was able to think about for example, the motion of a chunk of ice on a frozen lake, and to imagine what the motion of that chunk of ice would be if it could slide across the ice with little or no friction. And so, as a result of this mental ability, Galileo was able to come up with a very good idea of the correct relationship between force and motion. Newton, of course, those who have taken calculus or are currently taking calculus courses know that he was a co-inventor of differential calculus, and then, of course, the discoverer of the inverse square law of universal gravitation. And Newton was the one who took the initial ideas of Galileo and developed them into more systematic and quantitative statements that we call his laws of motion. And so let's just do a very brief survey of the laws of motion, and our understanding and application of these laws will be put to the test as we solve problems in this part of the course. So the first law, one way to state it is to say that an object moves with a constant velocity or remains at rest, which is simply a situation of velocity equal to zero, unless it's acted upon by a net external force. Now, what do we mean by a force? Another word for a force is an influence or an interaction that one agent brings about upon another upon an object. So an agent acting on an object provides a force. And the first law says that if there's not a net external force, then you've got a constant velocity. If there is a net external force, by implication, then the velocity is going to change. So this principle, called the law of inertia, first articulated in some form by Galileo, assumes that the proper connection is between the force acting on an object and the object's change in velocity, which we quantify, of course, as its acceleration. So rather than there being a one-to-one connection between a net force and a velocity, what Newton actually showed was that there's this one-to-one relationship between a net force and an acceleration, or a change in velocity. So, if an object therefore moves with a constant velocity, Newton's first law would tell us that the net external force acting on it is zero. It doesn't mean there aren't any forces acting on it. It simply means that the sum total of all of those forces is equal to zero. That's important for us to understand. The second law extends this insight from the first law to a quantitative statement, which says that the acceleration of the object is in the direction of the net force it experiences and is inversely proportional to this quantity that we call the mass. And the mass is a measure of inertia. Inertia means an object's resistance to having its state of motion changed. So, here's the way that we can express that quantitatively. That statement in words can be written down as the acceleration, and remember it's a vector because it has not only magnitude but direction. The acceleration is equal to the sum of all of the possible vector forces acting on the object divided by its mass. Right? Acceleration is proportional to the net force, and the proportionality constant is 1 over the mass. This summation notation, which you're probably familiar with, but just in case you're not, it means sum. It's the Greek letter sigma. And the index I simply means that there are a number of different forces potentially that could act on the object, and what we do is we add them all up. And so if we solve for that sum of all the forces, we get the more familiar form of Newton's second law, which is that the sum of the forces is equal to the mass times the acceleration. The first equation, though, on the left-hand side, to me makes more sense because A is the effect that is produced by the cause of having forces, net forces, acting on an object. So another way to understand this statement is that in some sense it's the definition of mass. It gives a quantitative definition of mass as the proportionality constant between the net force and the acceleration. So for a particular net force, an object that has a large mass is going to experience a smaller acceleration, and vice versa. An object with a small mass will experience a larger acceleration for the same net force that's being applied. The third law, okay, this says that all forces in nature occur in equal and opposite pairs. And this just has to do with the relationship between two objects that can interact with one another. If object A exerts a force on object B, then object B must exert an equal and an opposite force on object A. And I can draw a sketch to show this. We've got a ball and a block, A and B, and the force that B exerts on A is indicated with the arrow pointing to the left, while the force that A exerts on B is indicated by the arrow pointing to the right. And so both of these forces exist if A and B can interact with one another, and Newton's third law says that in fact these two forces are equal in magnitude and opposite in direction. Sometimes these kinds of forces are referred to as an action-reaction pair, because if A exerts a force on B, then B must also be exerting a force on A. Imagine pounding a nail with a hammer. All right, when you strike the head of the nail with the hammer is exerting a force on the nail. And yet at the same time, the nail is exerting a force on the hammer, right? Because the hammer's motion changes radically when it makes contact with the nail. That means the nail has exerted a force on the hammer to change its state of motion. At the same time, when the hammer hits the nail goes into the block of wood. And so its state of motion changes as well. And this principle, it's not so important initially when we first start just talking about Newton's second law and apply it to problems involving a single object. But quite often we will have more than one object in the same problem that exerts forces on one another. And the third law is very important because it helps us figure out what the relationship is between forces that are exerted on different objects. Okay, one important qualification about Newton's laws is important to keep in mind that Newton's laws are only valid in so-called inertial frames of reference. An inertial frame of reference is one that's not accelerating. So if you're driving in a car down the road at a constant speed and you're not turning, that means your velocity is constant and you're not accelerating. That is an inertial frame of reference. And for a person who's in that car, Newton's laws would be valid in the same form that we've just written them down. However, if one is, for example, in that same car and it's initially at rest and you press the gas pedal and now it's coming up to speed, so its velocity is increasing, that is a non-inertial reference frame because that object is accelerating. And so the take-home lesson here is simply that the accelerations and forces that we use to write down Newton's laws must be those measured by an observer that is in an inertial reference frame. And so for that car accelerating down the road, an observer standing and watching it from the side would be able to write down Newton's laws, but someone who's in the car would not be able to write them down in the form that we have them here. And that can sometimes be an important distinction. So common forces in nature. We're going to go through just a couple of them here, and there are some simple relationships that hold true for these. Weight is a common force in nature, and that's the force with which one object attracts another object, particularly a massive object like the Earth. So if an object with a mass m, such as a ball, is near the surface of the Earth, we know by our experience that it falls downward. And so it experiences a force from the Earth pulling it down towards the center of the Earth. And our experience shows us that the force that's associated with that situation is equal in magnitude to the mass of the object times a constant. And that constant g is simply what we mean by the Earth's gravitational acceleration. W represents the weight force, which is the force of the Earth pulling down on that mass. So that's what we mean by weight, and that's often a starting point in many problems for objects that are moving or even at rest near the Earth's surface. Another situation that commonly arises is when one object is resting on top of another object, or simply two objects that are in contact with one another. So the direction of a contact force is always perpendicular to the surface of contact. For this box sitting on the table, the surface of contact is a horizontal surface in my picture, and therefore there are contact forces that are perpendicular to that surface. And so if I wanted to write down the force of the table pushing up on the box, I would draw an arrow upwards. And because this force is perpendicular to the surface of contact, it's sometimes called a normal force, because normal is a synonym for perpendicular. At the same time, there is also, because the box and the table both exert forces on one another, then the box is pushing down on the table. And so there's a force of the box acting on the table, that would be downward, and we would call this n prime, because it's a normal force, but it is a different force from the n that's mentioned above. Of course, according to Newton's third law, these two forces, n and n prime, are equal to one another in magnitude and simply opposite in direction. And then one more situation that arises quite often is when we have a string or a rope connecting two objects. And a string, it's kind of like a very stiff spring, except that it can only exert a force or convey a force when it's in tension. So if you had a situation where the string was simply coiled up lying on the ground and was not being stretched, it doesn't exert a force. But if, as you see in my sketch, two masses are connected to a string and that string is wrapped around a pulley that's free to rotate, then that string being stretched is now conveying a force. And so the string results in a force upward acting on mass 1, and we will call that T1, and then T2 would be the force of that string acting upward on mass 2. And so T1 and T2 are those two forces acting on each of the two masses, and one thing to keep in mind is that if the mass of the string and if the mass of the pulley are very small compared to the masses m1 and m2, then the tension is essentially constant all along the length of the string. And so those two magnitudes are related to one another by being equal to each other. If, by contrast, if this pulley has a lot of mass to it, or if this is a thick string, and so as the object moves, there's more mass on one side of the pulley than the other one due to the string, then we would not be able to make this statement. But as a first approximation, in problems involving thin strings and very lightweight pulleys, we can assume that those two tensions are the same. So, our next step, having had an introduction, will be to move on to problem solving using Newton's laws, and I'll leave that for next time. See you in class.